Perfect. So the next speaker of the morning is Marie-Jeanne THORAVAL from the l'ADIX, from the École Polytechnique in Paris. So please, Marie-Jeanne, the floor is yours.
Thank you very much for the introduction, and thank you very much for the opportunity to present this wonderful program. So today I will talk about some drop impact problems, and I will make a little twist to it. I will put a bubble inside the drop before impact. So it's not cavitation bubble, it's just a normal gas bubble that we put before the impact. So usually when you look at drop impacts, you have this wide range of different applications that you can have for, we have seen for aircraft for problem of icing, can have some firefighting, some combustion, coatings, 3D printing. And here I would like to focus on two applications. So historically, the first people who looked at the impact of a drop containing a bubble were for this problem of thermal barrier coatings. Usually what they want to do is to deposit a thin layer of material at very high temperature onto a surface to make it resistant to very high temperatures. And they use a plasma spray. So they inject some small particles inside the spray. They melt the particles and they deposit on the surface. One of the issues that they have is that because particles can melt easily from the outside, but they get some inside of the particles that sometimes doesn't melt, so it can affect the quality of the deposition. So what they do is to use some empty particles, and then it's melting outside, and it's already fully liquid, and it's improving the quality of the thermal barrier coating. There's some other aspects that they see that the improvement of the quality, and they think it's because of the shape of the deposition and also the inclusion of the gas that helps protect against the heat transfer. And there is a second place where there is this problem of having droplets with bubble inside. So this is nice experiments of Klaas-Willem Wieser when he was in Harvard, and he was doing some printing of polymer forms where he would have a coaxial jet with air and liquid outside. And it would put some jet that would destabilize in the air, and that would deposit some droplets with a bubble, and that would form foam material and can then solidify with UV curing. So this is a method that can be used to produce some nice foam materials where you can control actually very finely the size of the bubbles. It is very difficult to do with the other techniques. This is the two main applications, and from this we are going to ask some questions on what are the usual questions that we have around droplet impact. So the geometry that we look at is we put a bubble inside the drop, we let it impact on a surface. It can be either solid surface or liquid pool. And the way we do that experimentally first is we put a coaxial needle where we put the liquid from one side, and we get a small needle inside to put the bubble. We inject it with a small pressure pulse so that the bubble can form, and then we release the droplet to impact on the surface. So this is the classical splashing that you observe with a silicone oil droplet on a solid surface. And when you put the bubble inside, and what you see on the right side here, this is the dynamics that you observe. So you get the formation of this vertical jet that is emerging at the center of the drop, even during the spreading of the drop. So it's very different from the jet that you observe from rebound, that is during the collapse of the drop. Here it's really during the spreading of the drop. So we try to do numerical simulations to understand this problem. So we use the code Basilisk that can do dynamic adaptive mesh refinement to capture the dynamics of the interface. And we compare with the experiments, and we are able to reproduce the formation of this vertical jet and most of the features. So we continued a bit more on the numerical side to study this problem. And we look at three different aspects. We look first at the maximum spreading of this drop, then how the bubble is affecting also the impact force, and finally we look at the impact on the pool to see whether the droplet will be able to go into the pool or if it will have some other dynamics during impact. So So the first thing we look at is spreading. So we have the similar spreading dynamics as a full drop, except that here we have some more complex dynamics at the center. But we focus here on the maximum spreading that we call beta, the ratio between the spreading diameter and the initial spreading of the drop. And we look at the maximum spreadings that we have here. And we characterize this for different liquids and different bubble sizes. And we first look from the simulation with full drop. So we use 3 different liquids with water and silicone oils of different viscosities. We see that there is, as the impact velocity increases, the maximum spreading diameter increases. You have a reduction of the spreading diameter when you increase the viscosity. If we put this in the series that was presented by Christophe yesterday, we have the 2 regimes of Weber and Reynolds numbers, and you have a nice collapse for the full drop. Now, if we put the bubble inside, you have the different curves here. We see that the presence of the bubble decreases the maximum spreading of the drop. And if we collapse, we see that the trend is very similar for the different liquids, but we would like to understand, to have some quantitative model to understand what's happening. So the first thing that we can guess is that there is already some decrease of the inertia of the drop because of the presence of the bubble. So this is the first thing that we can correct. So the diameter here is coming from the volume of the drop, so the inertia. So we can decrease this with prefactors that we put here. The 1 minus dB cubes, that is a reduction of the inertia simply due to the presence of the bubble. We see that by including this modified Weber number in the theory, we have an improvement already. So the curves are coming closer, but there is still some discrepancy. So the next thing that we need to understand is where is this additional effect coming from. And we have seen already that the dynamics is very different. Not all the inertia is going to the spreading of the drop. And we have some of the liquid that is going inside the jet at the center. So we can characterize this effect by looking at the radial velocity distribution at the time of maximum impact. And we measured the volume of liquid that has a positive radial velocity at the time of maximum spreading. And we can see that when you increase the impact velocity, you have the formation of the jet that has a converging velocity. And we can use this measurement of the volume that has a positive radial velocity to characterize the volume that is contributing to the maximum spreading of the drop. And if we do that, we see that there is some different dynamics at lower Weber numbers, but as you reach very high impact velocity, you don't have much dependence anymore. And if we use at high Weber number, the volume that is contributing to the spreading as a function of the size of the bubble, we see that this volume is decreasing as the size of the bubble is increasing. And we have a correction that we can fit with a prefactor that is about 1 minus dB cube again. So if we combine this one with the previous one, we have not only the first volume correction that we had before because of the presence of the bubble, but also this prefactors that is due to the formation of the jet at the center. And if we combine these two, then we get already a better collapse of the data by including a modified Weber number inside the theory. Now we still have some discrepancy. So the second part of the model is about the viscous regime, where we can expect also some effect of the bubble to change the dissipation in the drop. And if we look at the theory, so we have this maximum spreading that is to the power Reynolds to the 1/5. And we can introduce a prefactor. So there's 2 effects again. There is a decrease of the volume, but also another prefactor that we can measure. We can actually, in the simulations, measure the viscous dissipation that is happening inside the drop. And if we do that, we observe that there is a relative increase of the viscous dissipation. And we can fit that with this model here. And if we include this effect to a modified Reynolds number, we are able to make a scaling for all the conditions with a modified Weber number, so the 1 minus dB cubed to the square, and the modified Reynolds number. And we see that by including these two effects, we are finally able to get a good collapse of all the data. So we are able to understand the influence of the bubble on the maximum spreading by this modified model. Now I will switch to the impact force that is generated during impact. And there were some previous studies that were done for the full drop. So this is some of the experiments from Kéré. And they see that during impact, there is a very fast rise of the impact force and then a slow decay of the impact force. You can understand this as a transfer of momentum. And if you do this transfer of momentum, you get a scaling of the maximum impact force as the density times the radius to the square times the velocity to the square. And you can get simple understanding of the scaling with scaling arguments that is simply the multiplication of the dynamic pressure by the surface area, where you have a maximum when the area is reaching to the center. So this is how you obtain the scaling for a full drop. And this was verified in the experiments for different sizes of the drop, different surface tensions, and without any fitting parameters, they had very good comparison. If you include, that was done more recently, if you include some viscosity effects, then you can see that as you reach to lower Reynolds number, you have some significant increase in the impact force that is generated. And you can understand this variation with modification as Reynolds to the power minus 1/2 correction. And you can have also a correction that was done from the experiments of Lutzunzing and the simulations of Watzal from Twente, where you have also a correction from the surface tension. And you can obtain this by combining the impact pressure with the capillary pressure, multiply this by the surface area, and you get this Weber to the minus 1 correction at low Weber number. So it is what was done for full drops. Now we can look at what's happening for drop containing a bubble. So this time we put the bubble at the center. We look at the impact on the substrate, same with the basilisk. And we can see first for the full drop what's happening is that we have very high pressure that is generated at the center. Then you have separation of the peak pressure to two peaks where you have the impact around the bubble. And then you have very high pressure at the maximum, the peak force here that is spreaded over the impact region. When you increase the bubble, the initial dynamics is exactly the same. You get this very high pressure at the center. Then you have the splitting of the pressure, but at the maximum force, what you have is quite different with the presence of the bubble. Instead of having the pressure distributed all over the impacting drop, you have it only at the position below the liquid. So there is this cushioning effect from the bubble that limits the impact of the impact pressure to the side. So we can understand here what the effect of the bubble on the impact force. And we can put this in terms of quantitative time evolution. So we see here that the maximum pressure that is generated during impact actually doesn't really depend on the bubble. You get this very high pressure that is at the beginning, and then the decay in a very similar way. What's very different is that when you change the size of the bubble, at the beginning, if you have the full drop, you have very high pressure peak that is reached here. But as you increase the size of the bubble, you have a deviation from the force increase that is happening earlier and earlier to reach finally maximum impact force that is reduced. And if you measure systematically the maximum impact force that you have generated here for different impact conditions, you see, so first the curves that we saw before, you have the plateau at high Weber number for the full drop, and then the Weber correction at lower Weber numbers. And then when you increase the bubble size, you have this decrease of the maximum impact force. And you see that there is this tendency also at lower Weber numbers. So to understand this decrease, what we can do is to make a correction. So instead of taking the capillary force that is applied over the whole area of the drop. We apply a restriction here that is the maximum pressure is applied only in the region where there is liquid above. That corresponds to removing the part where there is a bubble. And if you apply this simple correction, you observe that there is a very good match with numerical simulations. So you can understand that the decay here is due to the bubbles that is preventing the large impact force at the center. There is still some discrepancy here at lower Weber numbers. We're still not sure what's happening, but the dynamics is probably a bit different due to the formation of the jet. So now I will switch to the impact on the pool. So the experiment here, so I will start from experiments. The experiments were done by master students, so it was quite heavy experiment. So we tried to combine two views. We tried to see the impact above the pool and to see also what's happening below the pool. So we need to have two high-speed cameras. The system to generate a droplet is quite difficult to have a good control of the pressure pulse, to have another third camera here to check that the bubble is actually in the drop. So this is what it looks like in the lab. So the student was operating herself, and it was very impressive results with a different part of the setup. And this is what it looks like, typical impact from above. And you can see that in this case, the bubble disappears, so it's probably going to the pool. And we characterize the size of the bubble. It's very difficult to control experimentally, so there is quite large noise in the size of the bubbles that is generated, but it's very reproducible. So we're still able to extract some interesting results. So we observe mostly three regimes as we increase the impact velocity. At lower impact velocity, we see that the bubble is actually going into the pool. So we still have the bubble intact after the impact. If you increase a bit further the impact velocity, you see that during impact you have the bursting of the bubble. And in that case, if you look from below, the bubble has disappeared. And if you go even to higher impact height, the bubble can even break before reaching the pool. In that case, you get a very nice jet at the center. And of course, below there is no bubble entrapped. And this is some of the dynamics that you can observe. A bursting bubble inside the flying droplet. It's a nice jetting phenomena. So this is different conditions. You have the encapsulation of the bubble at low impact velocity. You get bursting during impact, and finally the bursting before impact. As you increase the impact velocity, the viscosity has a stabilizing effect, so you can go to higher impact velocity to entrap the bubble into the pool. It was difficult to go further with the experiment, so we turned again to the simulations. So we can do, again, with Basilisk, and we can systematically change the impact velocity and the size of the bubble here. And we see that there is we focus here on the engulfment, and the same as the experiments. We see that at higher impact velocity, we can get bouncing of the drop with the bubble. Above certain velocity, we get a regime here where there is engulfment. The bubble will go into the pool. Finally, at higher impact velocity, you would get bursting. And we try to understand this transition. Usually for bouncing, you have a transition in terms of Weber number. But here, the Weber number is a bit modified because the impact velocity is resistance that you get from the surface. And here you have a deforming surface with a pool. So we turned and you can characterize the velocity of the front between the drop and the pool. This is usually for a full drop, about half of the impact velocity. But here, with the presence of the bubble, you get a different reduced velocity due to the lighter drop. And we use a theory of Radu that is looked at different density in the drop. And if you do the same with a drop containing a bubble, you can get a modified velocity for the interface between the drop and the pool. And now that you know that what the velocity of that is relevant for the impact in the Weber number, you can put it in your Weber number, and you get this dependence on the size of the bubble. And you can see that there is a nice transition captured by constant modified Weber number for the engulfment and the bouncing and the engulfment of the bubble. And this is, to understand the two boundaries here, it's related to the dynamics of the bubble. At lower impact, in these lower bubble sizes, the bubble will easily burst at the center. You get some deformation of the bubble that makes it more stable here. And eventually, you can get some bursting also on the side of the bubble, making it in a different bursting mechanism in this region here. So this is different aspects that we looked at for the impact of a drop containing a bubble. We looked at the maximum spreading, the impact force, and the encapsulation of the bubble for the impact on a pool. We looked also a bit of the velocity of the jet for different conditions. And this is some other studies where instead of putting some bubbles, we can put also some particles, immiscible fluids into drop. And just so this is just some nice movie of some other kind of jet that you can get, which is less axisymmetric, so it's a bit more difficult to study numerically. So that's where the experiments still come handful to understand dynamics. We don't understand what's happening, so this is still an open question. And another case where you put immiscible water drop inside oil, and you get also some very nice jets that can be generated in this configuration. Thank you for your attention.
Thank you very much, Marie-Jeanne. Now it's time for questions. I think I saw one first, then this one.
When the droplet impacts on a solid substrate and you have the bubble inside, I think your simulations, I would assume, were incompressible, right? Do you have a sort of intuition, or what would you expect if you would also consider the compressibility of the gas in the bubble? Because you see how the pressure rises as it impacts. Like you had this comparison where you see the single pressure point at impact, which then splits into two, pressure goes, yeah. So what would you expect would happen if you also consider the compressibility of the gas inside that bubble?
So THORAVAL has done some simulations, including the compressibility effect. From what I understand, it's the dominant effects, the dominant dynamics is very similar. For moderate impact velocities, you get he obtained some oscillations on the pressure due to the oscillation of the bubble, but the maximum. The main dynamic that you observe is similar.
Again, intuitively speaking, you have a bubble that has less inertia, so as the drop falls towards the solid wall, I would have expected the bubble to move up and pierce and hit the top drop wall. Actually, you showed at some point a jet piercing the top wall of the drop. Am I right in that?
Yeah. So,
but you didn't show that too much, yeah. You didn't elaborate on that.
So what's happening is that in free fall, the bubble will not feel gravity, so it would stay the same position during the fall. So the reason why the bubble still goes to the top is because it, as the velocity increases, the air drag becomes dominant. And then you have the relative gravity that increases during the fall, and then the bubble moves slowly to the top where it's bursting.
Well, the bubble doesn't feel gravity, but the liquid does. So
So in free fall, it will not. The gas and the liquid will fall exactly at the same velocity.
Okay, perhaps I'm missing something. I know from previous studies when there is an oscillatory disturbance, there are two modes of oscillation. There's either central mode or either in phase, where the bubble stays in the center, or out of phase, where the bubble is out of phase with the liquid surface. So it might actually, sometimes there's a central motion or it moves away. So I'm not sure that it will always stay in the center.
So I'm not sure what are these
But this
motions.
is when you send a pressure wave, a pressure disturbance in the liquid shell, there's a bubble inside. There are two types of motion. There's either two different modes. They either in phase, the bubble and the external surface. Of course, then I don't know what. Then you have a gas, liquid, gas. Depends on the material you have. There's either a central or a decentralized motion. The bubble approaches the interface. It doesn't always stay central.
So here you didn't mention, but the simulations are incompressible. We don't have any oscillation of the bubble. So
Yeah, okay.
it's not. There is no relative motion due to the dynamics of the bubble.
But still there's liquid inertia. Okay.
So beautiful talk, Marie-Jean. I actually had more or less the same question, but maybe as a follow-up. So how easy is it to control the position of the bubble inside the droplet in the experiment? Because that's a major thing, I think.
So that's why you have so much simulation in the talks, because it's difficult to control. So basically what we did, we had a similar problem for water drop in oil, but in that case the density difference is smaller, so we could find some trick to change the position of the drop at the beginning. But for the bubble it's very difficult, because the way the bubble is released is when it's the liquid pinches on the central needle. So usually the bubble tends to be at the top, but then you have also some oscillations of the liquid around that quickly damp, but at the beginning you're not sure exactly where is the bubble. So the answer is that we don't control anything in the experiment.
Yeah, so it's sheer luck where the bubble ends up. No, so it's but great experiments and really wonderful work. So it's thanks.
Good. More questions? Oh, well, let's thank Marie-Jean again.